Okay. All right, guys, so we're getting started, ready to get started here for our next presentation, and this is going to be on the Bryce Canyon contribution. Jason? And you're up.
All right, good morning. Can you all hear me? All right. My name is Jason Adrian, and we're very excited to share our Bryce Canyon storage server design with you today. So if we go to the next slide, Madhavan, Dominic, and myself, we're going to walk you through the design, what it is, and some of the unique aspects that we've been working on. So Bryce Canyon, it's a storage server design with 72 drives, but it's not a simple one configuration meets all. We're able to configure this as a single storage server with 72 drives, a dual storage server with 36 drives in each, or even configure it as a JBOD. So taking a step back, why did we build this? At Facebook, our workloads, they change over time. Every day is a new challenge. Every new product we introduce changes our workload behaviors. So we wanted to take a step back and say, what can we do differently? One of the main requests we got was to provide a higher power per slot compared to our previous Honey Badger design. At the same time, we really wanted to push the boundaries of thermal and power efficiency in our designs. One of the unique aspects of our Open Vault Knox design that we wanted to continue was the carrierless hard drive insertion and removal. So we made sure we kept that. And last but not least, we wanted a modular, future-proof design that we're able to swap out components at will, so we don't have to revamp the design every time a challenge presents itself in the future. So now, looking a little more at the details, we'll kind of walk you through the different components of this, and then we'll walk through some examples of how you can configure it, and then some of the unique aspects on the thermal and power. If we start in the back, you'll notice we have two fan modules in the back. Each has two fans within it. This is what cools the system. Down the center, we have a cable track, which allows us to pull the entire unit out of the rack on a set of rails and keep it on at all times for hot plug capability for our drives. We have the bus bar clip that we use in our other products as well, so this is compatible with OpenRack v2. In the front, we have our CPU modules. These are the Monolake CPU cards that you may be familiar with that we demonstrated last year as well. We have the drives on the left and the right-hand side. It's 6 drives deep by 6 wide on each side. We'll get to the logical representation of that in a bit. And then as far as the protocols, we have 2 cards in here, which we call our storage controller cards. These are meant to be protocol agnostic and allow us to change vendors or protocol at will. Along the front, which we've pulled off the sheet metal here, we have what we call our I/O modules. This is how we get data in and out of the box. This will be our network and any other interfaces to stream to downstream boxes. And again, you can see our hard drives and our carrierless latches here. All right. So from our front view, I talked a second ago about the single versus dual storage configurations to the servers. What we're highlighting here is if you were to configure it as 2 36-drive storage servers. So in yellow, we have our domain A. So it has 36 drives, and again, this is oriented front to back, not left to right. So we see 36 drives, we see our Monolake cards here, and the corresponding I/O module on the left-hand side. The backboard, again, has 36 drives, it has its Monolake up front, and the I/O modules here on the bottom right. So now if we take all the components out of the system and start looking at the boards and the components that make this up, along the bottom we have what we call our drive plane boards. Physically, it's built as 2 separate boards that are bolted together to allow us to have a smaller PCB assembly instead of one gigantic panel. This also allows us to have a cold air bypass that comes from underneath the system to cool the back rows of drives, because obviously in a dense system, you don't want the drives in the back getting very hot compared to the drives in the front. On the right-hand side, this is the Monolake card we mentioned that we've been leveraging from our compute team. We're able to take this as is and simply change out memory configurations to use it in a storage application instead of redesigning an entire new compute module for Bryce Canyon. This is where things get a little more unique to the Bryce Canyon. I mentioned earlier these storage controller cards, that we wanted something that would be protocol and vendor agnostic. Essentially, we take PCI Express coming in. We have a controller card, so in this configuration, you see a SAS IOC. We have a SAS expander to allow us to fan out to the 36 drives in that domain. In the case where we want to make this a JBOD, Or when we want to make it a 72 drive system where we don't need that second IOC, we can actually depopulate the IOC in the connector and create a simple JBOD expansion card. And at the top, you'll see we actually run 4 lanes out to a mini SAS HD, which lets you bridge the cards. Or as you'll see in future slides, how we can actually bring it to the outside world to create a JBOD out of the Bryce Canyon design. The I/O module, as I mentioned, this is how we get the data in and out of the system. Today we have 2 variants. If you split it down the middle and we look at the left-hand side is the same. In the back, we have our OpenBMC for systems management. And in the front left, we have our OCP mezzanine NIC. We have 8 lanes of Gen 3 routed to this, and we can support a 25 or 50 gig NIC at full line rate. On the right-hand side is where we have the more individual things. So the example on the left, we have 2 M.2 slots. Each are plumbed with a by 4 Gen 3, so we can put some NVMe SSDs in this box. On the right-hand example is if you want to exceed the 72 drives that are capable in that single system. We put a SAS controller there that allows us to get 2 external ports, so all 8 lanes routed out, so we can daisy chain to downstream JBODs. All right, next slide. All right, now I'm going to turn it over to Dominic to walk you through some of the different blocks in the system.
All right, so can everyone hear me? All right, so now that Jason's walked through all of the boards in the system, let's walk through the system from a conceptual level, like an architectural level. So the first thing to point out in this system, this is our dual storage server configuration system. And one thing you'll notice that's immediately apparent from the block diagram is that the system is mirrored. So we can just go through like the first half of the system. And unfortunately, you don't actually see the drive plane board, just poor color choice. But all of these boards connect through the drive plane board. And so let's walking through from the top, let's go through the compute module. So you have your CPU, your onboard boot SSD, and your memory. From there, the connection to the drive goes through the storage controller card. So we have 8 lanes of PCIe Gen 3 going through the drive plane board into the storage controller card. So the storage controller card houses a SAS IOC, and out of that is 8 lanes of 12 gigabit SAS into a SAS expander. And out of the SAS expander, we have 36 lanes of 12 gigabit SAS or 6 gig SATA to 36 hard drives. Again, out of the connector of the storage controller card into the drive plane board. To the front of the system, again, we have our I/O module here. And this houses our BMC. But from that, additionally, we also have 2 M.2s, each of which is plumbed with 4 lanes of PCIe Gen 3. And to the outside world, we have support for the OCP mezzanine. So we have a 25 or 50 gig NIC, which is supplied by 8 lanes of PCIe Gen 3. And so in the next few slides, what I'm going to walk through is what Jason actually mentioned was that we have several variants of the IOM and the storage controller card. Now, depending on how you populate them in the system and what you choose to populate, you can have several different configurations. So next slide. So this is what I just presented in the last slide. So everything's the same. This kind of just shows how we're going to populate it into the rack. So with OpenRack v2 in this specific form factor, we can add up to 8 of them in the system. Now, so on the next slide. So if you choose to not populate the compute module, and correspondingly you don't populate the I/O module because it doesn't need connectivity to the outside world, what we do here is we have the variant of the storage controller card where the IOC is not populated. Now, there's an internal mini SAS HD connector on each of the storage controller cards, which we use to cable from the primary storage controller card over to the secondary with a small internal cable. Now, that's how you have one compute module talking to 72 hard drives in a box. Now, we can take that to a more extreme. So let's say you want your compute outside of the box, right? Next slide, we don't populate either compute module. So you don't have either of the I/O modules. Now, before we had the storage controller card variant that didn't have the IOC, we just populate 2 of them. Now, the internal mini SAS HD connector, instead of cabling from one to the other, we have a provision in the front of the system where you have a drop-in-place replacement with 2 external mini SAS HD connectors and you just cable that to the storage controller cards. Next slide. Now briefly talking about thermal performance, one of the challenges with building a box like this is that you have a lot of drives in line. And one of the concerns is that you have thermal shadowing. So what you see here is very preliminary thermal profiling data from a test that we ran where we stressed every major component of the system and just saw how it performed. If you note here, it's kind of hard to see, but between drives, the rows 3 and 4, with 1 being on your far left-hand side, you notice some kind of funky stuff going on here with the numbers. So what we actually did here is we have a cold air bypass between these 2 rows. So if you imagine the front of the system, you have your drive plane boards and then your I/O modules underneath. So what we actually do is we have space underneath the drive plane boards and a cutout between drive rows 3 and 4. So the thought here is that you take fairly cold air from the cold aisle, duct it underneath the drive plane boards, and mix it between these 2 rows. So you can see that our thermal performance is actually pretty good. And moving on to the next slide, I'll leave it to Madhavan.
All right. So can I get a show of hands? How many people went to the booth and checked out Bryce Canyon yesterday? Got plenty of folks. So this is going to be a repeat for you guys, but for the benefit of others, I'm going to spend some more time on serviceability of Bryce Canyon, online serviceability. So hard drives are hot swappable, and we kept the same carrierless design as in the previous generation of storage servers. As you can see in the picture, let me get my laser pointer. I got it. So as you can see, each hard disk comes with a latch. You depress the green button, pop up the latch, and you tug it gently to pull the hard drive out of the slot. There is tension built into the latch to hold the hard drive in place. That way it doesn't fall down and crush something on the PCB, as well as it also enables us to take out the HDD for hot swapping it. One thing to note is it is carrierless, so it definitely keeps the costs low, and this vertical design helps us to populate the drives in a dense fashion. As you know, it's 72 drives per slot, per chassis. This shows the front view of Bryce Canyon. Before we get to hot swapping the drives, Bryce Canyon, the front portion, this shows the front view of the chassis. It's held inside a sheet metal tub. This needs to be ejected out to access the hard drives. So as you can see, we're all gamers at heart. We have 2 joysticks in front, the 2 buttons. So you depress the buttons, pull it out, and then you can hot swap the hard drives. So the tub is held inside the rack with these 2 notches, and the levers, one on each side of the chassis, will help unplug the whole tub out of the rack for servicing as well. This shows the back side of the chassis. These are 2 fan trays, as Jason mentioned in the previous first few slides. It's easy to replace, thumb latch, pull it out, and as you can see, there are 2 fan modules inside each fan tray. These are 2 dual rotor counter rotating fans, and these fans are also hot swappable. Next slide, please. So this is the more interesting slide. So as far as advancements goes, this is the quantitative explanation of improvement from previous gen to Bryce Canyon. So in a 4U chassis, we fit 72 drives, but working it out to 1 rack unit, 1 open rack unit, these are the numbers. It's about 20% improvement in drive capacity. This is the total HDDs per rack. As you can see, we have warm storage and cold storage split it out. In cold storage, it's dramatically higher because we replace a power shelf. We don't need 2 power shelves in the rack, as Dominic showed previously. We'll use only 1 power shelf, and that gives the extra space for 1 more Bryce Canyon and 72 more drives to be populated in. CPU as well. As you all know, Honey Badger is out there, and it's been servicing. It's been great. It uses a lower-end CPU. For the purposes of today, we need a higher-end CPU. So we're going to roughly 6x. These are estimates based on our workloads. And the memory is also increased. So this is the max capability of the monolith, 128 gigabytes of DDR4 memory. As far as NVMe slots goes, on the warm storage, we do have capability to bring out 8 lanes of PCI Gen 3, 4 to each M.2 slot. On the cold storage, we don't have the M.2 slots. We use the same 8 lanes of PCIe to bring it out to a I/O controller, so you can fan out to additional JBODs, as it was previously mentioned. SAS SATA, these are the comparisons. We support 12 gigabits SAS and 6 gigabits SATA, and the network bandwidth is also increased. We now have 8 lanes of PCI Gen 3, so we can support up to 50 gigabits line rate. We can support 100 gigabit NIC over there, but it's going to be bottlenecked by the PCIe throughput. Last slide. So last slide, Bryce Canyon supports OpenBMC. I think there was a presentation just before this in some other room regarding OpenBMC. I'm not sure if you guys caught a lot of that. So OpenBMC unifies a lot of stuff across our platforms. It supports thermal sensor readouts, a lot of system monitoring, including power consumption. It supports, this is FRU-ID, field replaceable unit. There's utilities bundled into OpenBMC to power cycle, to remote service a system, to collect logs from a system. A lot of really good capability that's been ported into Bryce Canyon OpenBMC as well. So for more information, you can check out OpenBMC link given here. You can also Google it to find the link. And that's the summary. We are open to questions if you have any.
Is the CPU module based on Broadwell DE, or?
This is the exact same.
So just, since it's going to be impractical to have a mic going around, could you repeat the question because we're recording?
Sure. The question was, is the CPU module using Broadwell DE CPU? So this is the standard vanilla monolake that's been discussed. So we are porting in the same processor into our system as well.
So I got a question back there.
Can you talk about your storage infrastructure? Are you compressing, encrypting, anything, the data before you store and decrypting while?
So so the question is, can we talk about the storage infrastructure and encryption? That is not part of the talk today, so that would be a different group of people that could talk about that. We're focused mostly on the platform and the hardware enablement of that. But if you have any questions on capabilities of the platform, we could certainly answer some of that. Sure.
A question on the warm versus the cold storage using the M.2. There didn't seem to be a difference in the bandwidth. Is that mostly the latency caching on the M.2?
So sorry, the question was about why we don't have the M.2s and the bandwidth is the same? Is that what you're?
Well, so you showed the bandwidth be the same essentially for the cold and the warm storage option, but one includes the M.2, so it's got some flash memory there. Is that mainly impacted the latency to cache a frequent access, or what are you doing?
So in a warm storage style of data, you can use it for caching or write coalescing. For our cold storage, I mean, the goal of an archival application is less in the latency, more on just getting that power down to the lowest and the cost down. So the latency impact is a little bit different there. So we're not looking at very small IOs. It's more of a sequential archival workload. Does that answer the question? No. Okay. We can talk further after this if you want.
I think we got a question there.
How many drives are powered on at a time in cold storage?
So there's a difference on how we implement our cold storage. Oh, sorry, to repeat the question. How many drives are powered on in a cold storage application in the Bryce Canyon? So the system itself is able to power them all up at the same time. There's no difference in the chassis itself. The difference is how many power supplies and power shelves you install in the system. So in our case, we may put one power supply, which will give us 3.3 kilowatts for the entire rack. So that would limit your max number of drives that can be powered on at once. We may choose to even use less than that in our application because our software has a very particular series of events that it's looking to do in its drive power cycling. Sure.
Do you guys have any problem with your high density enclosure managing drive performance next to your fans?
All right, so the question is performance in a high density enclosure, especially due to fans. The answer is yes. I mean, that's obviously a very important characteristic of a dense chassis. We do have I don't know if you saw the top-down view, we keep a several-inch plenum in the back for our airflow, which also gives us some distance from the fan modules themselves. We have made some changes through our initial designs to reduce some of the noise and vibration coupling from the fans into the system. As it is, the fans themselves are mounted on elastomers, and that entire module also has some isolation from the chassis itself. So from a physical vibration, we have double isolation. And then from the acoustic side, we have a few changes and design aspects that we've put in there. We may have time for one or two last questions. So when we showed a warm versus a cold storage, the question is, what is the difference in warm and cold? We were mostly highlighting this as an example. This is not a very specific software implementation. When we think warm storage, more of an online type of application, you may have small I/O, large I/O. The M.2s certainly give you the ability to do like a write-back cache, things like that. In a cold application, you're typically not as concerned with very small I/Os either on the write or the read paths. So that's kind of why we were showing two different examples. It's not tied to a specific workload.
3 quick questions. 1, no SES. 2, the X4 is pretty low bandwidth. Is that for cold storage only? At 110 megabytes a second. 3, have you got space for dual link?
Sorry, can you repeat the last two one more time?
SES, X4 bandwidth, and future monolink.
So it's a second. Are you asking, do we support SCSI enclosure services?
Yep.
Yes, we do. And the second was, sorry, the last question.
The X4 bandwidth is that?
The by 4 of 12 gigabit?
Yeah.
Is the question, is that enough?
It's low. I assume that's for cold storage application.
Even for a warm storage, so that's a decent amount of bandwidth, at least for our use cases. If you start putting an SSD in there versus a rotating platter, you may start seeing some challenges there, but with a rotating-based platform, it seems to be enough for our use case. It will differ in others, but in the type configuration where we showed the two 36 drive servers, we actually have a by 8 that goes from the SAS controller to the expander of 12 gigabit SAS.
The last question was the height for your new V70 follow-on V2 or the follow-on monolink. Your space to fit that in.
To be determined, but the intent is to have it future compatible with new CPU modules. Any last questions? And if you want to talk to us at the booth, anyone with a Facebook shirt, come see us at the booth, ask some questions, take a look at the system, and engage in the conversation. We'd love to share the design with you.
All right. Thank you.
Thank you.
Thank you.